All right, welcome back. So we are on and finishing chapter 1. Here's a magnetic circuit, and this is pretty common. What you're going to see is we have a magnetic material, like in the case of a transformer. And because it's dependent upon the dimensions, it's not an AWG, we are going to try to give you some specific dimensions. This is my AutoCAD skills, right? You see the 3D with the dashed lines, so you get a sense of what's going on. But I got a coil of wire with approximately 400 turns in here. I've got all these dimensions going in that direction, the depth, the height. You can take a look in more details, but these are all in meters. I would like to find phi for a beta of 0.5T just in this center leg, right? Because this here is going to have a flux density, but once it departs here, it's going to go in parallel. So the rest of these strings are going to have a lower flux density and a lower value of flux, just like in the current, right? If I had a circuit here where I had a current source and I had two parallel legs, coming out of the current source is going to be a lot more current than going into the parallel legs, right? Just from an analogy standpoint. And we're going to assume all the flux that is in the core stays in the core, and all the flux that's generated from those turns of windings is going to be linked by or picked up by the magnetic core. So the first thing we need to do is calculate the area of this center leg, so 0.08, and then 0.08 in the back. So again, we're just getting the perpendicular direction to the flux. That's why it's this way and this way. We're going to include the length when we're trying to figure out MMF and all that stuff. But this here has a flux density of 0.5 T. So the actual flux is going to be my flux density times my area. And the unit for flux is Webers. So 3.2 times 10 to the minus 3 Webers. We'll come back to that problem. And the reason why we have to come back to that problem is based on the fact that magnets aren't all that good of magnetic material conductor. We talked about like some of the world's best magnets are only 50,000 times more magnetically conductive than air. And the same thing would also apply to electric circuits if we were not concerned about heating them up, and that's that they would get saturated, right? If you try to keep pushing electrons through a piece of wire, you can only push so much before the resistance starts to build up, right? That's the concept of saturation. So it's much more prevalent in magnetic circuits because, again, the conductors that we have are very poor for magnets. So it has a linear region. We have this knee point here, and then another linear region, which basically says I can put very little magnetic field here, and my flux density goes up pretty high, pretty quickly. Once I start getting to this point, it becomes non-linear, this knee point. So now I got to start driving a lot more magnetic field to get flux density, because I've got so many of the north and south poles. Does everybody understand how you get a north and a south? You learned that in physics? No?
Yeah, but I don't remember.
So basically, how do you make a magnet? Run a current through it? No?
Yeah, no, you wrap the wire around it.
You get a magnetic field around it, and you direct that in a specific orientation. And if you run that at a high enough level, when you remove the magnet, it stays north in one direction and south in the other direction. So essentially, you're aligning the poles. So you might have a north and a south and a south and a north and a south and a north. They might all be all over the place. When you're done, they would all be lined up. And the more magnetic field you apply to it, the higher the level of magnet is. The way to unmagnetize material, there's two ways to do it. First one, you can throw it in an oven. If you get it hot enough, unless it melts the metal, obviously, you'll lose magnetism. Also, if you drop them, sometimes just that jarring motion just messes up the poles. So either one of those are ways of demagnetizing them. So why do we put this here? Because depending on your magnetic field, your field intensity, if you're in this linear region, you can characterize it. If you are in this knee point region, you actually have to look at the curve to pull off the points, just like you did when you did electronics, right? For those of you, anybody here take 342 and finish it, 343? Did you ever look at the curve points and do it, or did you just say, let's find the Q point? And because finding the Q point is essentially that.
Yeah.
So you actually did it off the graphs to figure out operation?
Not normally, but you have to understand that you can't.
Okay. You do that sometimes in, electronic circuits. You have to do it in magnetic circuits. No ifs, ands, or buts around it. So let's look at saturation. So we're going to use this magnetization curve. It's on page 22 of the book. I think it's on the book. We want to find the reluctance in each leg that's necessary to do that. So remember, we have 3.2 times 10 to the minus 3 Webers here, and 0.5 Tesla, which means we have 0.25 Tesla in the outer legs, right? So if you look at my flux density, I have 0.5 in the center leg and 0.25 in the outer legs, right? So that flux is splitting in two, which means its flux density is also splitting in two, as long as the areas are the same. So from this curve, and this is where you need the curve, because my H value is going to be determined based on the magnetic material. And you can see here, I need 50 amp turns per meter in the side legs for H, and 70 amp turns per meter in the center leg. Yes, sir?
I think I missed what our example was. Are we talking about a transformer?
This example.
Okay. There's center and outside legs there?
This is the center leg, and these are the outside. Right, so this has all the same flux density. These two have the same flux density, but they're in half of the center leg. Right? Okay, so now we have that. Now we're able to start to calculate what the reluctance is. But before we do that, we're going to draw our magnetic circuit. So we have a bunch of power sources, right, or energy sources that is necessary to deliver the MMF. So I've got 70 amp turns going through 0.24 meters, right? And what I did here is I said, okay, let's just cut the center in half. So this is 0.16, 0.08 in half is 0.04, another 0.04 here, that's how you get the 0.24. So my MMF to drive that 70 amp turns in the center leg is this value. The two outer legs, because they're in parallel, right, the current sort of dives off. So essentially what I'm doing is I'm figuring out what the voltage source needs to be able to deliver the power that is necessary to get those magnetic field intensities. So my MMF that I actually need here to draw or drive that magnetic field is 34.8 amp turns. So it's essentially trying to figure out what is the voltage here, right? Because I got to get this voltage drop plus these voltage drops, right? Does everybody see what I'm doing? This is the voltage drop here. I don't care about the voltage drop at this point. I want to know what this is minus the plus. So I need this voltage drop plus the voltage drop that's across those two reluctances. That's why I'm adding them up like that. Yes, sir?
So where'd you get the 0.24 and I get that
The 0.24?
Yeah. Was that from?
What's the length of this center leg?
Okay.
It's 0.24. So it's 0.16 here, another 0.04 here, and another 0.04 here.
Oh, okay. Okay.
Just the center. Then the side legs are going to be at the center point, out and back. And so that's how you end up with a 0.72. And since they're in parallel, right, just like resistors in parallel, they reduce the resistance by the parallel combination. So I can either do it as a function of the reluctance, or I can do it as the distance, right? Rho times L over A. If rho and A are staying constant, then it's just L in parallel with L. That's what I'm doing here. So the actual voltage that I need to drive that 0.5 Tesla to the center is 34.8 amp turns. Okay? Make sense? You can say no.
What does MMF stand for?
Magnetomotive force. So we have a voltage source in AC and DC circuits, which provides a current, right, which drives a current. We need to drive a magnetic flux through here. So the magnetomotive flux source is that value, and that's what we're calculating for, the actual magnetic energy source. And if you remember, this is this amp turns. Well, I have to drive 38.8 amp turns through here. So that's why by adding more turns, I can get by with less and less current. Yes, sir?
What does it mean for like 7 amp turns?
What do you mean, what does it mean?
Like, what is that representing? Is it representing like revolutions or something?
Nope. Nope. It's just essentially what your intensity is of your magnetic field, so how strong of a magnetic field you're producing. And it's dependent on the material type, because this material, if it was highly magnetic or really good magnetic conductor, you might actually have a much lower value to be able to deliver the 0.5 T, because it's so conductive to magnetic energy. Okay? So now I know what my voltage is, right? I solve for my current, so I only needed 32.8. For my magnet motive flux, I've got 400 turns, so I need 87 milliamps of current through that coil of wire to give me my 0.5 T. All right? So there's two ways you can do it. You can either bump up the current or add more turns, whichever you want. Most of the time you see more turns because magnet wire is cheap, right? Anybody know what magnet wire is? You want to explain it, or?
I don't know. We used it on a project for PLCs last semester. It allows, when you run a current through it, allows a pretty impressive magnetic field.
Well, sort of. So the only difference between magnet wire and regular wire is the insulation. So magnet wire is designed to basically be run on top of each other. I could not run two wires touching each other, right? Because why would I run all my way that leg when I could just bypass it that way?
Just copper with a lacquer on it.
Exactly. It's copper with an insulation. So they actually put a very thin level of insulation, lacquer, if you buy magnet wire, because the voltage difference between here is, a tenth of a volt, or 0.3 volts. It's a very low voltage. So magnet wire is just regular wire, but a very thin insulation. That's all. It's the only difference. How you get the magnetic field is I run many, many turns through a core, and then I can get lots and lots of magnetic energy. Okay? So to find my reluctance, this equation here is just my amp turns times the distance divided by Weber, right, by phi. So the voltage divided by the current is going to give me my reluctance of my center leg, and then the reluctance of the two outer legs. All right, questions on that? It's exactly the same for magnetic circuits. Exactly the same as electric circuits. All right.
Ask a question about the homework.
Sure.
So you have us start off. One thing, would you mind drawing what it kind of looks like?
Drawing what kind of looks like?
On the magnetic question, the circuit you have, or I guess it's a.
Drawing what the actual circuit is, or?
I don't know. I have it right here if you want it.
Well, I can put it up on the board, so I don't have to draw anything.
Well, it's just you just described it with words.
Well, let's see if I can point, because I'm not 100% sure I'm following, and that's my fault, not yours. So, oops, wrong class. Okay. So what part?
I'm not really sure. Is this just a circle core, or is it are we supposed to look at it as a circle core, or sort of like that?
It doesn't matter, because I've given you the length of the flux path through the steel. I tell you what it is.
Okay.
And I tell you what the area is.
So with the first question being the air gap reluctance,
Yep.
how do you go about finding that? And if you don't know what kind of current you're putting through? You give us the flux.
I don't care about the current. The air gap is only going to see magnetic energy, right? You don't have current flowing through a gap. So if I'm trying to show, you've got flux going through the air. You've got a wire driving a current which forces a flux. So this is I, and that's phi. So the flux actually jumps through the air gap. The current, you don't have any current in here. And you shouldn't, right? You don't want current going through the air. So does that?
Where I'm getting lost is how would you solve for reluctance if you're not?
It's the same process. You have a magnetic circuit. You find the voltage source, reluctance of the metal, reluctance of the air gap, reluctance of the metal. Right? This is a voltage source, a resistor, another resistor, and a third resistor. And the current flow through that circuit is how you're going to calculate or help calculate what the reluctance is. Okay? Does that answer your question?
Yes. I think I was just not looking at it right.
The only reason why I put this curve up is because you have to have the flux density and the field intensity to be able to do that. It's specific on the steel.
I know I may be asking a lot, but would you be able to describe how you go about doing that?
Sure.
Because how I got it was I went all the way to the top, assuming that it was 1.75 meters squared, and I ended up at 7,000, which was maxing it out.
No, it's not that high. No.
Okay.
It's the same approach here, right? We figured out what the amp turns are going to be for a flux density. So once we have the flux density, we can pull off those values. This curve is flux density, right? See, on the x-axis it's B. I mean, on the y-axis it's B. And on the x-axis it's magnetic intensity. So if you look at the problem description, if a flux of blank Webers is needed, you know what the Webers are, right? You can do the cross-sectional area to get the flux density. Once you have the flux density, you can get the field intensity based on those legs, and then just walk through the problem that way.
Awesome, thank you. I couldn't make that connection.
That's okay. That's why it wasn't assigned. Good question. Any other questions on that?
Is this due this Thursday?
Next Tuesday.
Next Tuesday?
We'll finish this up and we'll do next Tuesday.
Okay, so the homework's not due Thursday? Tuesday.
I give you a week to do it.
Okay.
I would say I think we're finishing covering all of it.
Yeah, that last slide pretty much covers it though. This one we're going to not get into too much details, but it's pretty useful for us as we talk about electric circuits moving forward. But without getting into a lot of details, you can calculate what induced voltages are, like on a transformer. And again, it's opposing the changes in flux. So we're going to generate a voltage based on the number of turns and that changing magnetic flux. So this applies for transformers, but it also applies for motor generator sets. So this d phi dt is a way to calculate how this voltage, and we talked about this in another class, is a concept called back EMF. For motors or rotational systems, you get a back EMF based on this induced voltage. That's the actual voltage that's created because of this changing flux. We actually can change it to say this is just for one flux that's being linked. We can sum those all. Then we can get our total induced voltage, which is going to be a function of this d phi dt, which is our flux linkages. So we only really are interested in not the changing flux. It really has to be linked flux. Flux that's actually being detected in a wire. You can change flux all you want, but if you don't actually monitor that with that wire, you pick it up, it's not going to work. So most of the time what you'll see, and did anybody here take 351?
Magnetic.
ECE 351, yeah, with Mauricio?
Yeah.
Did he talk about flux linkages? That's typically how you refer to things.
Yes.
Okay.
That's one of the most difficult classes in
Yes.
any program.
It's the hardest class. Just wait till you take the graduate level of that one. It's even worse.
I'm not doing that.
So that's the flux linkages. We'll talk about induced force of the wire, so you can use your right-hand rule. And this is really just a vector calculus, and so a lot of us haven't had that. So how do I get A crossed into B? All I'm trying to do is get an orthogonal vector. Does anybody know what orthogonal means? Another fancy way to say perpendicular. If I have two fingers pointing this way, this is orthogonal, right? So what you do is you point one finger in this direction, the other one in this one, and if you're flexible enough, your thumb, because I'm not, your thumb will point in the orthogonal direction. So this right-hand rule is basically just giving you the orthogonal direction of the force. So if I have a force, I am not flexible enough, so I like to use my fingers. Current stays in the wire, doesn't move. Put my current in this one. Rotate in the direction of the magnetic field. So this magnetic field is into the page. So I rotate my fingers, my thumb points in the direction of force. This is another concept of orthogonal, right? So this one's a little less flexible. So I can get the flux on a wire by using this right-hand rule. And that's it for chapter 1. That's pretty much all the electromagnetics that, at least to give you an understanding, a basic understanding of how induction and motors and generators work. It's all magnetics. All our mechanical energy, well, almost all. Again, these classes always dovetail, but almost every ounce of mechanical energy is transferred with a magnetic field. Okay?
So that's how you get it between mechanical and electrical.
Yep. Or vice versa. That's the nice thing about mechanical, the magnetic field. This doesn't care. You can go mechanical to electrical or electrical to mechanical. It doesn't care. As long as the basic physics are being met, you're good to go. Questions on Appendix A or Chapter 1? Are we moving too fast, too slow? Good speed? Yes, sir.
I personally haven't taken physics 2 yet, so flux density and how to calculate, the cross-sectional area of that. Right over my head.
Well, how to calculate cross-sectional area?
Or not cross-sectional area, but how to calculate flux density and the turns. And
Yep.
Can we do an example of something like that, or?
That one that we put on the board is not sufficient. I mean, I don't have one prepared, so the numbers I'd have to do something with a calculator or something like that. But there's a bunch of examples in your book. I just didn't bring the book with me.
Okay.
Ultimately, all you need to do is just look at the concepts of electric circuit. How do I get my voltage source? How do I get my resistance? How do I get my flux? It's all the same. And we're just simplifying everything down by saying everything is going to be perpendicular and linked. So it's more straightforward. So what I would say is the equations you want to sort of memorize are pretty much all here. You've got your H, B, and phi in here. And you have your MMF and reluctance equations in here. That's pretty much it. To go between the two, though, right? Like this one shows that these are perfectly linear, right? The H to the B is perfectly linear. It is not. So this is for an ideal case. That means you never have saturation. That's not the case. So that's why we use the charts to go from B or H to B in here. We need the actual plots.
That assumes no flux escapes the core.
Right.
Okay.
And that's not realistic in the real world, but if you design a motor or an inductor that is designed to have some leakage flux, that's not always desired. Although in transformer design, it might be. Anybody want to guess as to why?
Why you'd want flux leakage?
Yeah, why would you want flux to be leaked, not picked up?
Transformer is trying to step it up or step it down, and it's trying to step it down and it's leaking, and that's not as bad, right?
No, that's just based on the turns ratio. If you turn it up or down, you go from there. But why would you want to have more or less magnetic energy leaking or not?
Cheaper to build based off the geometry.
Partly of the cheaper to build, yep.
Is it the efficiency?
No, because flux is just energy, right? It's not energy, it's magnetic energy, so you're not affecting your efficiency.
Well, you can round the corners if they're squares and whatnot, because you know that.
That makes it more linked, but how or why would you want to do it? Well, a perfect example is, Here's into campus, right? If I have Bangor Hydro, which is big bad Bangor Hydro, and I'm connecting over here and I get a fault, I get tons and tons of energy here, right? If this is at 0 ohms. So by putting this at 10 ohms, you limit the fault current. So a lot of times you actually specify the impedance to knock down the level of fault current of your system. It also has to do with what's called stability of a system for bigger generators, but more often than not, you specify some of these transformer sizes to say, I want to knock down the level of fault current. And I did a job a long time ago for Harvard. Well, it was for NGrid at the time, but for Harvard University. Harvard, anybody know where Harvard is?
Cambridge.
Cambridge, it's a very stiff system. You don't see a lot of electrical lines, but coming in from NSTAR actually is a really, really strong signal or system. And they had, I think, 3 or 4 lines going to campus. The fault currents on this were so high, Harvard had to put in reactors to knock down the fault current. They had over 10,000 amps of available current at each distribution circuit. And if you have more than 10,000 amps, most distribution devices won't be able to interrupt it. So what you do, you put an inductor there, I can't remember the size of them, and it doesn't consume any real energy. It's reactive energy, but it knocks down the fault current. So sometimes if it's a really strong system like you're in New York and you got 10 feeders going into a line, you've got lots and lots of fault current, you just put a reactor in there and that knocks the fault current to a much more manageable level. So you actually buy fault interrupting or fault limiting devices of reactors, never resistors. Because if you had a resistor, right, I squared R, Harvard's going to pay just to knock down the fault current, could be millions of dollars a year, or you put a reactor in there and it messes with your power factor, but as long as you don't have too much inductive load, you're fine.
Can you balance it out later down the line?
You can boost the voltage because all this is really going to do is knock down the fault current, but it also decreases the voltage. So usually what happens is you run your system voltage a little higher than nominal, and then that way you can account for any voltage drops in those inductors. But I only know about this because the system that they had there, you can take a look. These are old G&W, and I think I have pictures someplace. These old G&W oil switches. These things look like this is big mechanical linkage, and I don't know. People must have had a lot of courage. They actually had to open them manually by hand. So you're standing in front of these. These are independent poles, and it's got the 3 lines coming off, and you get this mechanical handle, and it's 4160, and it looks like probably a bullet that's maybe by 100 times bigger, and that's how you would open the poles. Praying the thing doesn't explode in your face. They used to do stuff, I don't know how they did. I mean, it's amazing that the electrical system got built because the stuff that you see is just scary. And some of that stuff is still in service. It's too expensive to replace it. You go around campus here, does anybody know in Barrows, if you want to get electrocuted, we have live 4160 volt inside Barrows. If I had a special key, I could introduce you to 4160 if anybody's interested. You could walk up and touch it. Swear to God.
What?
Inside the basement of Barrows is live 4160 that you could walk up and touch. If you don't believe me, go outside my office and there's a door that says 4160. Nobody has keys. I have a key that opens up all the offices essentially in the building. It doesn't open that door. Because inside there are 3 pole-mounted transformers, not mounted on a pole, mounted basically in, on like desks essentially. So you have 3-phase 4160 coming in, steps it down to I think it's 208. So you could walk right up if it's energized and you could access the live 4160. You just walk right up to it.
It's open air?
They're pole-mounted transformers. They're designed to be up 35 feet in the air. So what you see up in the on the top of a pole, that's walking distance. So I mean, that's perfectly available to you if you had the key.
There's no code or anything against that?
When was Barrows built?
You don't have to update it?
No.
Grandfather.
Well, it also too is you can actually have. So when I went to this is in Western Mass, but they actually have live 345 kV that's inside of a building. This transformer that steps up from, is it 20 kV probably 20, maybe 15 kV, I'm not sure, up to 345 kV is inside, it's indoors. It's inside of a mountain, and if you could get up tall enough to the top of the transformers, you could physically come into contact with it. So the National Electric Code doesn't apply when you're talking about industrial facilities or under lock and key. That's why Steve Moody, who's the head electrician, he's the one who has a key to that room, and maybe a couple other electricians. And I had to go in there once to get some data off it, so I've been in there once in the 16 years that I've been here. But that's how it used to be, because if you ran 4160 in the building, you could get by with really small cable, right? If anybody pays attention to the new ESRB, the Barrows building, well, new, it's not new, but it's kind of new. They have 5,000 amp service at 208 volts. You probably have 500 MCM conductors per phase. Whereas if you had the 4160 volt transformer right there, you could run in just regular, like number 4-aught wire is all you would need to be able to handle that current. So that's why you put things, that's why they used to do things in the basement. Some of the dorms are that way too. All the new stuff though, they put the transformer outside because of fire, right? Because if you have an oil-filled transformer sitting in an electric room, now you've got a fire issue. Even though the oil is really hard to catch on fire. Has anybody here ever tried to start a fire with gasoline?
Yes.
It just blows up, right? Anybody ever tried motor oil? You start it and it just kind of like, just hanging out, because it just doesn't have a lot, it doesn't vaporize. This mineral oil, basically, it's very hard to start, so it's like a really low burning flame. It's just really slow. It's like diesel. If you light diesel on fire, it burns, but it's not a crazy fire. It's the same thing. So all this mineral oil is fire retardant. And they actually have what are called dry type transformers they could put inside, but those are a lot more expensive than oil filled ones. So that's why outside of New Barrows, behind, does anybody know where the diesel is that feeds New Barrows? It's between Neville and Barrows. There's a transformer right there, and then they run inside to the new electric room in Barrows. We probably could get a tour of that if anybody wants to see it. Steve could open it up.
Is there any gas insulated systems on campus?
No. Gas insulated, if anybody's wondering. So if you get high voltage stuff and you don't have a lot of space in room, you can't use air, so you use SF6, sulfa hexafluoride, which is a really good insulator. So typically you'll see GIS is the nickname for it in really tight spaces. Like if you're in New York City and you don't have a lot of real estate, you can't run 345 live, so they run it in GIS, and that provides the insulator, so you can run them within a couple feet of each other, and it's safe to do that. So GIS would only be for higher voltages, 115, 130, 345 kV, like those breakers would be GIS. I think even 35 kV, those might be SF6, or they could be vacuum. Depends if it's outside.
Yeah, I feel like it would be more vacuum for 34.
Pardon?
I feel like it'd be more vacuum for 34.
I'm trying to think, because I've done some projects for CMP and I thought those were SF6, but I could be wrong. The nice thing about Well, the nice thing about SF6 is you can just keep a bottle of SF6 and it always pressurizes the contactor, where if it's a vacuum, if you get a leak, you can't open it. So that's part of the problem. I'm old enough that when I worked at Maine Yankee, they had air blasts for 4160. So these were these huge breakers that weighed 5,000 pounds, because in the back, they actually had concrete arc chutes. So when you interrupt, you have to blow the arc into an area that's not going to catch on fire. So they had these massive concrete arc dissipation devices, and they would weigh, I don't know, thousands of pounds, and that was the idea. They would just keep things going. So
Those worm gear operated ones?
yep,
That's what we had, the worm gear.
yep.
We had 34, 345, and 115 coming in. Then in the 4160.
345. Usually those are, if it's a really old one, those would be oil circuit breakers. The 345 kV breakers were concrete arc charts. Usually they'd be up in the air. They would just blow it up in the air.
No, when we were down at the 4160 breakers.
Yes, those would be concrete.
Yeah.
Now you can't buy those. It's all vacuum
Oh, really?
or SF6. Yeah, if anybody's interested, you could take a look at GE, Cutler Hammer. They have a tremendous amount of information of how breakers actually interrupt. And anything over 1,000 volts is almost definitely going to be a vacuum, up until about 35 kV. Usually 15 kV, but after that, it could be vacuum or SF6. Anything above that is usually SF6. It's so much cheaper. If anybody's interested, you could talk to me about that after class. Got all kinds of useless information on that, so.
Some arc shoot videos.
Yes. Well, I always tell people, and I think I told this class, I mean, that's arc is the most dangerous one. That's how you die, and you die painfully. Getting burned is a lot more painful than getting electrocuted.
It's the suits just keep your body together, right?
No, so arc flash suits, so it's basically anybody here walking around in their underwear outside today? Why not?
It's cold.
So what are you doing? You put layers of clothing to insulate you between the cold temperature and your body temperature. Wouldn't that also apply to heat?
It's not the pressures.
You can do pressures, but there's nothing you can do about pressure. It's all calories per centimeter squared, which is energy.
Okay, that's right.
So it's heat. So when you have multiple layers, and you can go category 4 for arc flash, the whole purpose is really just an insulating barrier. That's all it is. You have a shield to keep you from going blind, and then you usually have hearing protection in because the explosion, it can make you deaf. I've actually seen somebody who went across a DC system, and he didn't get hurt because he just dropped a wrench through it, but he was blind. He couldn't see for I don't know how long, and so he had to go to the hospital. And then they fired him at the hospital because he wasn't working smart. So
He destroyed a wrench.
he destroyed a wrench. He didn't destroy the battery. The battery system could put tens of thousands of amp. That laughs at a wrench. That socket or wrench just evaporated, and he was walking around like this after, and he couldn't see. But arc flash is the dangerous one. So if you ever work at a place, make sure you get some FR gear and really pay attention, because it wasn't that long ago that nobody cared until people started getting burned. You can watch videos of people in front of a cabinet and then this big fire explosion, and they run out, they're on fire. And it's exacerbated because anybody here wear Polypro?
Sticks to your skin, melts right in.
It melts, yeah, it melts, and it's plastic, so depending on the heat, it could actually keep the fire going. So
I had that happen to me. I was on my four-wheeler and I was wearing a type of poly sweatpants.
Yeah.
And I was right up against the exhaust and it melted into my back of my leg.
ow.
That's unpleasant.
But natural fibers basically are self-extinguishing, so wool, cotton, if you're a player, silk, right? All those are really good for doing insulating. Most of the time it's cotton, but you got to be careful too with cotton because you need a really tight weave. Like this shirt has a pretty tight weave, and you can look up and you can see there's a lot of threads. It's like the Egyptian thread count. The more threads per square inch, the harder it is for the air to escape through. So that's why you use a very high thread count. And then they also treat it with a flame retardant material on there. But if you feel FR, and we have some in the basement if anybody wants to feel it, it's kind of scratchy, but if you look at the thread count, it's really, really high. I'm surprised the Navy doesn't make you guys wear FR gear as an electrician.
Well, they switched it over because there was a chief on one of the carriers that reached in, touched 4160. He died instantly, but his whole, we call them poopy suits, the coveralls, his whole poopy suit was like welded to his body.
Yeah.
So they didn't want to, it's kind of gross, but they couldn't peel it off his skin.
Yeah. Well, at that point he's dead, so it's
Yeah.
unfortunate, but why bother? So
Yeah, it was for like funeral purposes
Yeah.
and stuff.
most of the time if you work in electric rooms, or if any of you work on site, you definitely want to think about getting all cotton gear. Don't show up in shorts because you have exposed skin. It's amazing to me where we've done site tours and people will show up wearing, I'm thinking of somebody who did last year, showed up to an electrical facility wearing shorts. It's like, hello, this is the bad example in case something yourself. And that's the number one thing, and I'll get back to this at some other point, but who is the ultimate person responsible for your safety? You. Somebody tells you to do something, you better make sure you know what you're doing because they might get in trouble, but you're in pain. So you've got to protect yourself. So FR gear, they also make electric boots now, electrically insulated boots. That you can get those. So if I'm going to go on the field, that's the first purchase I would make is good FR clothing and a pair of fire-rated boots. Hey, might as well keep yourself safe. Leather gloves.
It hurts.
What's that?
It hurts to get shot.
Yeah, I've been zapped at 120 right at the panel, which doesn't seem like a lot, but you definitely feel it. And that's the most. I'm like, that's enough for me. I don't want to be shocked any harder than that. Anybody here, a friend of yours rubs their arm on a door and then they touch you? That's the thing, but multiply it by a certain amount of time, it just lasts. Well, even on a ship, right? It's going to be the scariest thing because you're in a submarine. Hey, don't touch anything metal. Okay, where do I stand? Right?
We'll put rubber mats over everything.
Yeah.
You're standing on rubber, it's all around you. You got a rubber mat on you, rubber sleeves up to your arms, face shield, hearing protection, and then you have a guide tied to you,
To pull you out.
pull you out when you get stuck.
Yeah.
And then they teach you, like, if he's not letting go, drop kick him, whatever it takes to get him off.
Don't touch them.
Yeah. Just be in the air.
Because you get electrocuted too. Well, the thing is too, and this is on, I don't know if it's on all Navy ships, but there's no such thing as automatic control. Everything is done sort of manually, and you got to be able to manually rack things in and out and open and close things. And so you're standing in front of the switchgear saying close, and
The main breakers,
Yeah.
you can operate remotely, but most of them,
you got to go out to the panel and open it up, and
there's water everywhere, oil everywhere. It's fun.
yeah, just doing a good job selling it.
Yeah.
Well, they say the worst thing too is when a ship goes out after it's been in dock for a little while, because when you heat everything up, all that oil is burning off, and it just smoke, and it burns your eyes, and you can't breathe. But supposedly there's nothing you can do.
You're out to sea.
Yeah, but it's like if they would, could you just run it for, could you go start the car and let it warm up and get all that stuff off, and tell that to your CEO, and he's like, get back in here, All right, Chapter 2, Transformers. So we talk a lot about Transformers because they save our bacon. And if it wasn't for Transformers, we'd still all be living downtown New York City, or we would be without power because you could not run DC at any appreciable distance without having some significant line losses, which mean you had low voltage and you had to pay a lot. So DC is what killed Thomas Edison's dream, right? Even though Thomas Edison tried to convince people it was more dangerous for AC, he actually electrocuted dogs and elephants and stuff. He was a pretty cruel guy if you read some of the stuff.
He invented the electric chair to
Yeah.
get rid of AC, right?
Yep. And I don't think it matters whether it's DC or AC, but that's, we won't get into that. I'll get myself into trouble, but DC to AC was really where it's at. We might switch back. It may take many years, but they make solid state transformers. Why can't you just use a buck boost converter or some switching devices to go ahead and get upper, higher or lower voltages just with power electronics? And if you had control, right, like with a DC to AC, if you're doing this with power electronics, you actually can say, I want power in this direction or not. A transformer does not have that ability to determine. It has the ability to determine it, but it doesn't tell any information. So maybe not today, maybe not in 10 years, but possibly, we'll have microgrids where everything would be DC. If you got a solar system or PV or fuel cells, you could do everything with DC and it work exceedingly well. People have heard, right, NECIC, New England Clean Energy Connect, that's the DC line they're talking about adding that goes in from Quebec Hydro through Maine into Boston, because Boston has committed to buying 90% of that, I don't know the exact number, but a lot more green power in 10 years than they currently do. And there was a line that was going to come through Vermont or New Hampshire, and then that got shut down by the residents of those states. So they're proposing this New England Clean Energy Connect. So, but it's a DC because of some advantages to it. Transformers are great. They are super duper efficient. There's no rotating parts, right? So you don't have to worry about bearings and all that stuff. Super reliable. Transformers are designed to operate for 40 years, and most of them can operate a lot longer than that. What do we do? Well, the biggest one probably is impedance, or equipment electrical isolation. How would it feel if you were at your house and you can actually do this? You can actually do what's called an auto transformer and essentially go from 12.47 K to 240 volts. This is not electrically isolated, right? These two are connected to the same point. So if there's a fault somehow through the transformer, you've got 12.47 going into your house. So having that electrical isolation, if I actually have a transformer, and these two, there's no electrical connection between the two, right? This is all magnetic energy. If I have a ground over here, right, and a ground over here, what happens? Nothing. There's no path for the electrons to flow through and continue on that path. So having this electrical isolation is really a big benefit because nobody would want to connect their house if they had the possibility of being energized at that value. I think I talked about this class. You're the audio guy, right? So
Sure.
why not, right? You can buy speakers, 4 ohms, 6 ohms, 8 ohms. Does anybody know what that means?
That's the DCR.
Keep going, keep talking.
Oh,
DC resistance?
yeah,
I don't know if that's a DC resistance. It could
it
be.
is.
It is.
But it's the impedance, right, associated with the speakers.
Yeah.
And the output of your amplifier should have the exact same impedance. Why?
It'll break it, you know.
No?
Current handling capabilities of the amp.
Nope.
Less power consumption.
Nope.
Because you like numbers being the same.
Yeah, that makes it easier.
I usually ignore it and just go for it anyway.
Well, if you actually did that, your performance would be reduced because when does max power transfer occur? When your source impedance matches your load impedance. So if you wanted to get the most performance in terms of volume, you can deliver the most power when the speaker matches the output resistance of the amplifier. So really fancy amplifiers, you can select 4 ohms, 6 ohms, 8 ohms, and then you can match it to whatever your speaker. What are they ultimately doing? They're just changing the taps on a transformer. That's all they're doing. They're being sneaky. So higher quality ones actually have that transformer in the output stage. The cheaper ones don't. I mean, if you go like mine, in my office, it's fairly heavy. It probably weighs 15 pounds. Anybody pick up an amplifier today, they weigh nothing because it's all just power electronics. There's no quality. But then you can do Dolby NR 52 or whatever, or 7.1. I mean, you can do so much more with this stuff today. But they last for 3 years, right? I mean,
An amplifier and a receiver built into one from like 1995, and I bought it like 2 days ago, and it's like 20 pounds.
yeah. Old stuff, that's what they did. If anybody is really into hi-fi and you want to be cool and impress all your friends, get Macintosh equipment. Anybody heard that brand? Made out of New York, still made in New York. It's like, you can buy like the bookshelf speaker system. It's $2,000 for bookshelf, but it's really good quality stuff, and people are in the know. They're going to be like, yeah, I'm impressed. That's good stuff.
Some more college loans for that.
Get some more college loans? Yeah. They make speakers and amps and turntables, but they make really,
Just wait till they're 20 years old and buy them for dirt cheap.
that's true, but wait, you can't find them really. Because I've looked in the past.
Specifically, but
Oh, the older brands like the RCAs and
Onkyo, Sony,
yeah.
Bose,
I, s-
basic stuff like that.
I want my Mac though. Those are cool, and it's Macintosh. It's MC, not MAC.
Yeah.
But take a look. They're made in New York. They're really cool. So instrument transformers. An instrument transformer, its whole purpose in life is to take a higher voltage, like 345 kV, and step it down to a much more manageable voltage, like 115 kV, so you can send that from the substation on the high tension lines into your relays or your control. And it does it exceedingly accurately. So these are just transducers. They're converting high voltage to manageable low voltage, or high current to low current. You see these a lot in the utility industry because we can't handle, 345,000 volts going into a box that's maybe 6 by 6. We can't handle 4,000 amps going into a box that's 6 by 6. So we just step them down to much more manageable levels, and we would do that. And then power transformers, again, all they're doing is they're taking input power and outputting essentially the same output power, but they're doing it at different voltage levels. So those are the major uses. Here's a sort of a fancy, and these are really hard to find, but if you're trying to make a really fancy one, like, again, I always go to the Navy because I actually had a chance to go to Annapolis, to this fancy testing lab, and you actually walked in, it was a copper room because they want the Soviets to steal information about what they were doing. So you walked in, it was all lined up with copper. But you can actually get back feeding information through this line because there's some capacitance to ground, right? You actually have a path through those wires because there's capacitance. Except, in this case, this is what's called a Faraday shield. So any energy, electric field, magnetic fields that exist outside here all get shunted to ground. So this is a very fancy isolation transformer because it takes all that excess energy and dumps it to ground. So you have no impact whatsoever between primary and secondary. There's no capacitance, there's nothing. So this is the higher end equipment electrical isolation. We talked about this for max power transfer, ZL equals ZTH. If you buy the speakers, usually you can't change the impedance on speakers, at least that I'm aware of. Maybe you can, but I don't know anybody. So you have to be able to reflect the impedance from the load to the source to match it up. Let's see, do I have an example? Let me see if I have an example of max power transfer. Where is max power transfer? Ooh.
What's the TH subscript?
TH subscript? Where are you talking?
ZL equal to ZTH.
Oh, Z Thevenin. Who loves MATLAB?
We had to design transformers on MATLAB.
Yeah. Well, I'm going to just do a brute force approach. I've got a 24 volt source, and I've got a 8 ohm source impedance. And then I'm going to try a bunch of different load resistors. I'm going to go from 1 to 12 to figure out where does max power transfer occur. Okay? So I'm just going to do brute force. I'm basically going to say, take my voltage, divide by R load plus R source. So if I'm looking at my circuit schematic, I have, here's my source, here's R source, and then external to that is our load. You do that all the time, right? Does anybody here use the, I know they used to do this for Agilents, but we have the Reguls. I don't know what ECE does. But do you ever have to go into your AC function generators and adjust your source impedance? No? Sometimes you enter in a voltage in your source impedance and it doesn't match. It doesn't match what you specified it as, and the reason being is because it's trying to predict what the voltage needs to be internally to give you a desired voltage on the output. That's essentially what they're doing. They know exactly what their source impedance is, and they're trying to predict based on your load. So oftentimes when you do a function generator, you have to go in and say an infinite load impedance. So basically this voltage here is going to be the same on the terminals regardless of the load, as long as the load is small enough. So I'm trying to go ahead and just brute force it. I've got a vector called R load, which has 1 through 12. This is just a fancy way to say how many elements are in R load, because I want to run a for loop for as many elements that are here. Then I is just V over R. And I'm indexing from here by using this N. So this is position 1, 2, 3, just matching up the numbers. Then I'm going to put my power of my speaker, and I'm going to keep track of it by saying it's I squared N times R. I'm going to run through that for loop, and then I'm going to plot it. Does this syntax look different? Have you done for loops and while loops? Right? For L for N equals 1 to 1,000, or N equals 1 to 10. Do these steps until you reach the end of the for loop. And in MATLAB, you just have to index it. And so at the end, I'm just going to plot it. So where do you think max power transfer is going to occur?
8.
Is that 8?
Yeah.
So this is 5, right? X is 5, which is X is 5 ohms. 6, 7, so it's getting pretty close, 17.92. And 8 is at 18, so it's not a huge difference. Now you think, hey, let's keep increasing the resistance and go up. This is 9, and it is less than 18, right? 17.9. So this is just a brute force way to prove max power transfer, which says your source impedance and your load impedance have to be the same, or your Thevenin equivalent impedance, right? So that's why we can have a really complicated source, but that is your R Thevenin, or what we'll learn in this class, you also have Z Thevenin, which is your Thevenin equivalent impedance magnitude. We'll talk more about that. Okay, any questions on our MATLAB script?
Why'd you have to use length?
Because what if I wanted to go, instead of stopping at 12, what if I want to stop at 50? By using the length command, it automates the process. I don't have to keep track of the number of terms in the vector. It'll just automatically do it for me.
Okay, so it just takes everything in our load and then stops.
No, what it does is it says, this here has 12 elements. What if it has 24? I want to run my for loop for all 24 elements. So by using this length, it automatically adjusts the for loop so that it runs through all the elements.
Okay.
So it's just a sneaky way to say let n equal 1 to 12, but not knowing that it's actually 12.
Okay, so
Because I could put in 13, right?
then you get that 13.
And if I just put for n equals 1 to 13, or 1 to 12, then it would skip that last element. But if I do it here, you'll actually see that there's an element at 13. So it does it automatically for you. That's a nice thing. This is why I like doing MATLAB, because it keeps me honest, and this is, I think, the first time we've done it. My handwriting is not the best. You don't have to worry about handwriting here, right? It's all just typed out. And it basically says we have to do this approach. So there's nothing up my sleeves and saying, well, you were sneaky about it. This actually walks you through the process. So moving forward in the semester, we'll do a lot of stuff in MATLAB instead of using the calculator and doing it on the board, so that you can follow through with the steps. It makes it a little bit easier. Okay? But it looks very similar to your calculator. It's just using slightly different commands. Yes, sir?
So I've never really used MATLAB before. I see it's kind of like a coding language, but
Yep.
do you have to like do any like define commands or
No.
main program?
This is the main program.
It's just pretty much just start coding what you want
Yep.
to do.
Because MATLAB has a built-in engine that has like the sine, cosine, tangent, the square term. It has all that stuff built into it. So you don't have to, like in C, you have to load the libraries, right? The, what is it, load.h or whatever the heck there. You don't do that. It's all built into the engine. It's defined.
Yeah.
How do you load the libraries to say, okay, I need the, like there used to be a one for math, that you had to do the sines, cosines, you would define math.h? Okay, I didn't realize. But that basically has all the built-in math functions in C, so that you can call a function called cosine or sine, and as long as you pass it the right parameters, it would do it. It's the same thing in MATLAB. If I go to MATLAB workspace, where is,
Automatically does it though.
well, if I type over here, I type cosine, so it actually is a function call.
Oh, okay. So you can just pretty much type help and then what you're trying to do.
Yep.
And it'll give you like a.
It'll give you a little bit of information, but it's just a function call. So like when you do a cosine in C programming, you're calling a cosine function that has been defined. MATLAB does the same thing.
You can also put libraries into MATLAB if you.
You can create functions.
Oh, it's not. Okay.
I don't know if you can do actual libraries. Maybe you can. I'm not that sophisticated, but you could write your own code that says Rob, and you pass it some arguments and it calculates it back. Like one of the things people like to do is rectangular to polar, or polar to rectangular, or radians to degrees. Some of those things, you just build them yourself and then you just call them. Yep. So it's very easy to do in MATLAB. Here's an instrument transformer. And I don't remember if I talked about it in this class. I teach 3 classes, and sometimes the material overlaps, so I apologize. But a current transformer has a wire. It's located around a wire. So this is a donut CT. Anybody want to guess as to why? Kind of looks like a donut, right? Yeah. So you've got the donut CT. This is a magnetically conductive material. So this has iron or some metal that's conductive. You've got some turns of wire in here. So this is your secondary wire. Your current going through this wire, this is going up in this direction, is going to induce current flow in the secondary of this element. And because the turns here, there's a lot of turns, this current's going to be reduced. I keep saying turns. Every transformer has to have 2 windings at minimum, right? A primary and a secondary. Where's the primary winding? The wire itself. All you need to do to have a winding is to get a magnetic field to be picked up in your core. This is creating a magnetic field, right? So this is my primary winding. It just has a turns of 1. This has a turns of whatever you need it to be, and you multiply the number of turns, which is going to reduce the current. So it's the opposite of voltage. So that's how I get an instrument transformer. Okay? A voltage transformer, or a PT, potential transformer, sometimes called a CCVT, capacitively coupled voltage transformer. It doesn't work on the same concept of regular transformer, but all it is just a power transformer that's super duper accurate. So whatever voltage that you apply on the primary, it replicates that pretty darn precisely on the secondary. Okay? So those are the concept of instrument transformers. That's why we have a CT and a PT or a VT. Those are the only instrument transformers we have. Here's a power transformer. I don't know the size. I got this off the web. I can't remember. But this is pretty common for an oil-filled transformer. This is called a conservator tank. This transformer, if you can't tell, is filled with oil. Look at the bolting, and there's a gasket here. Oil is the best insulating medium as well as cooling medium that there is for transformers. The reason why it's the best is because if the oil gets hot, it rises to the top and then gets directed to these radiators where it's allowed to cool and go back to the bottom. So you don't have this dry type insulation that's not moving and it's always getting at a high temperature. The oil will move through. And in some cases, not many, I've actually never seen one, you can actually force the oil through the transformer to increase the rating of it. This one actually has forced cooling. You see you have radiators here, right? Those are fins just to reject heat. But if it's too hot or there's too much current going through it, you kick on the fans. You turn the fans on and it just blows air through the radiators to help with cooling. The conservator tank, this thing is partially filled all the way up here with oil. And on top of it is a bellows, or maybe not even a bellows, it could just be oil. But then you have a nitrogen blanket, and that nitrogen blanket basically keeps a constant pressure. So if there's a burp in the system, it can absorb into this tank without having the welds or the gaskets to fail. It can absorb small changes in pressure in this tank. What's that?
It's like an oil catch can.
It is, but it's not. You don't actually have. Everything is under pressure, so the can basically will come and go. This one actually will. This one's not open to the environment. So inside this control panel is this little. This could be here. I don't know, but this right here would be where the gas bottle is filled in. So you have nitrogen. Yes, sir.
Do you ever have to change the oil? I know it's not covered.
You have to change the oil or the nitrogen?
The oil that's
Yes.
used to cool off it.
You don't often do it, but if you are some reason get a bad indication, you may want to change the oil because it's degraded to the point where it's no longer any good. Maybe you push the transformer too hard and the higher heating has destroyed the oil. That's a possibility. It's not very often, but you can see here you've got a drain and a fill. And actually, these transformers are pretty heavy. They're always shipped empty, right? Because you're limited to what, 100,000 pounds on a trailer? Doesn't take long with some oil to get to 100,000 pounds. So these are always shipped under vacuum. Well, actually under slightly positive pressure, again with nitrogen. Why do I have nitrogen? I keep saying that.
It's inert.
It's inert. So nitrogen doesn't mix with the oil. You don't have to worry about air, which has water and all this other stuff in it. So it's all under pressure. Can you tell if this is Y or delta transformer?
Yes.
Which is it?
I'm just assuming you can because you're asking.
I'm just asking a question.
Is it a Y?
Delta, because there's a neutral?
Does delta have a neutral?
I can't remember which one has a neutral.
Why does?
Y has a neutral, and this has how many bushings? If it's a delta, you only have 3 bushings, right? A, B, C. A, B, C, and then the neutral. So this would be a Y. I can't tell. I can see 1 over here, 2, 3, but I don't know if that's another one. It's hard to tell with this image. So power transformer, very common. This figure I stole from our previous material. This is an ideal transformer. It's the same concept that we use with magnetic energy. It's a primary winding, a secondary winding, and we get a flux flowing through the core. Current in, flux, right? We take our fingers pointing in the direction of current, wrap, our thumb points to the direction of flux. It circulates around, and then it comes back. Notice this has a primary voltage, which is at a higher voltage, and a secondary, which is a lower voltage. So we have more turns on the primary than we do on the secondary. What we're going to find is this transformer is designed to step down the voltage, and we'll see why in a minute. But also when we looked at the CTs, remember we only had one turn of winding on the primary and many on the secondary? This is the opposite, right? So this is going to decrease the voltage on this side, but increase the current. Okay? We oftentimes, because we like to work with schematics, we don't like to work with a box like this, so we'll work with a schematic. So the transformer is just a bunch of coils, and they are facing each other. That's the difference between an inductor and a transformer. The transformer has two sets. This one shows the two straight lines. That would usually indicate that it's an iron core transformer. There's some sort of metal. You can go with air core, and in that case, you would have nothing in here. What we're going to use this semester is just the air core representation, and we'll just assume it's always iron. Primary voltage, primary turns, primary current, secondary, secondary, secondary. The rule of thumb, all right, primary voltage, all that means is it's not the higher voltage winding, it's where the power is coming from. It's coming from the primary side and being delivered and sent out on the secondary side. So most cases the primary winding is in fact the high voltage winding, right? Because most of the time we're stepping down. But for a generator step-up transformer, the generator is operating at 4160 and it wants to send it out at the distribution level at 115 kV. So that would actually be 4160, and then the secondary would be 115. So primary and secondary only has to do with power in and power out. That's a better representation. Okay, so this is going to get us into our concept of a turns ratio. So if you remember back in the when we just covered this today, VP equals number of turns on the primary side times d phi dt, or the flux linkages. We can do the same thing on the secondary. Vs equals ns d phi dt. The flux, right, this is just a series circuit, so the flux in here is always the same. Ideal transformer. So d phi dt, I can solve for that and set those equal to each other. So d phi dt is equal to Vs over Ns, and d phi dt is Vp over Np, so I can set those equal to each other. Solve for Np over Ns, and that is defined as our turns ratio. Number of primary turns to the number of secondary turns. Okay? So if you actually buy a transformer, you'll get the turns ratio because you actually don't care what the turns are on the transformer. What you care about is it's a 4160 to 115 kV. 4160 to 115 kV. That tells you the number the turns ratio. I don't need to know what the number of turns are. That's not relevant. So you never buy a 30 to 300 turn transformer. You buy a 4160 to 115 kV transformer. And then that is analogous to the same turns. If we are talking about ideal transformers, we're going to use the concept that power in equals power out. So there's no loss of power in the transformer. So we're going to say power in, which is VPIP, and power out, which is VSIS. And then we're going to just go ahead and do a little bit of math. And what do we see? The current is opposite. The turns ratio is VP over VS. But for current, it's the opposite. Does that make sense? It damn well better, because if VP over VS was the same as IP over IS, would it be constant power? No, it wouldn't, right? Because we want the current, the voltage to go, let's say it's a step-down transformer, we want the voltage to go down, and the only way for the power to be constant is the current goes up, right? So they have to be the inverse of each other, otherwise it wouldn't be a constant power device. Yes, sir?
So would that change from a power transformer to a current transformer? Because I
Nope.
said the winding. Okay.
Same exact thing, because the current transformer is a power transformer. This is just that turn on the primary side, just a turn of 1. So it's exactly the same. And then we can also do that for impedance, for reflecting impedances. So normally what we like to do is we like to reflect this impedance, which has we can use a Thevenin approach. If I know the voltage across the impedance plus the current through it, I can get the voltage. So if I want to step the impedance on the secondary side, which is ZS, I can just say that's equal to VS over IS. So I'm over here. The ZS that's over here, the load, is just the voltage drop across it divided by the current. And then I just substitute in my turns ratio, VP over A, AIP, do some math, and what do I get? I reflect my impedance from secondary to primary by using the square of the turns ratio. Okay? That's important that you use the square. So going back and forth to reflect impedances, you just use the square. All right? If you're confused and you're not sure which way to go, you can always go back to, think about your house. Remember coming in on the pole, I have a transformer and here's my house. Maybe you have 100 amps going into your house. How much current should you have over here? A hell of a lot less current, right? Because if you had more current over here, then why would you even have the transformer to begin with? So over here, you might actually have 2 amps of current for your house. So if I take this transformer out and I want to represent this house, this is 240 volts, right? So the resistance is 240 divided by 100 is 2.4. What if this is 12.5 kV? I still want the power to be constant, right? So should the current, should the resistance go up or down? Up big time, right? R should be much, much greater because I want to only get 2 amps over here, right? So 12,500 volts divided by a really big resistor will give me 2 amps. So your house looks like noise, right? And most of the fuses that you see on a distribution circuit, the reason why we use fuses is because a breaker can't detect those, because going to your house, you might look like half an amp, if that. So if you look at, you're going down the street and you look at distribution circuit that's peeling off on the main street, you'll see there's usually a fuse cutout. That fuse might be 3, sometimes 5 amps, and that's all you need to run to an entire neighborhood. Okay? That's how we do the turns ratio. We'll pick this one up on Thursday. Have a great day.